Welcome to the Walton Pi. What you're about to see is a test review for a calculus class that covered implicit differentiation, rates of change, the mean value theorem, Lhopitals Rule, and so on. This test review comprises sections of my Calculus is a Piece of Pi series going from 3.11 through 4.9 with the exception of 4.5. And there we go. Okay, so the idea of related rates is that oftentimes different things that we would like to be measuring are interrelated and connected to each other. So if we are doing stuff with related rates, what we can do is we need to find some way that the two variables that we are looking at, or know and don't know, have some way of being connected to each other. So for example, if we have a, let's see, like for example, we have a balloon that is inflating. So we are inflating some balloon and we are pretending that this is a perfectly spherical balloon. What we could know is we could say, well, if we blow, let's see, 1 liter of air each minute, what is the rate the radius increases at, I don't know, 5 minutes. So it's a very large balloon, but we are blowing in a full liter of air every minute, and we want to figure out what's the rate the radius is increasing at 5 minutes. What we have to do is we have to find some way to connect the two things that we care about. So liter, this is some volume, and then we need to have a way to connect that to the radius. Well, in this particular example, there is the formula that volume of a sphere is 4/3 pi r cubed. And so this is a direct connection between volume and radius. And then at this point, this is now a implicit differentiation problem, where we are going to take the derivative of everything with respect to time. So this is going to give us, we got dv dt is equal to a 4 pi r squared times dr dt. So this is the derivative of both sides, and this is giving us a connection between the rate that our volume is changing, which is 1 liter, and the rate that our radius is changing. So it's 1 liter is 4 pi r squared times dr dt, which is what we would like to find. So we want to know what is this, so we can solve for it. And the way we're going to be going about doing that is we can divide both sides by the 4 pi r squared. So we get dr dt is equal to 1 over 4 pi r squared. What we now have to figure out is we have to figure out what is r, and this is where we go back to, we know that we are looking at it at 5 minutes. So our volume has been increasing for 5 minutes. That means that we know that our volume is going to be 5 liters is 4/3 pi r cubed. And so solving for r, we are going to be able to see that r cubed is 5 divided by 4/3 pi, which is 15 over 4 pi. And so that means that r is the cube root of both sides. So dr dt is going to be 1 over 4 pi times the cube root of 15 over 4 pi squared. And we could do some simplification on that, but that is going to be what the what dr dt is going to be. So in this particular example, we were lucky in that there was a direct connection between the two. But then at the same time, we might have ran into a situation where we were trying to figure out the rate the surface area changes. And there isn't a very easy connection between volume and surface area. So if we were to do that same problem, but instead be saying that we have our balloon, it's increasing, and our dV dt, so the rate the volume changes is going to be still that 1 liter per minute, but we are trying to figure out what's the rate the surface area changes. This is going to have to use what we know about volume and surface area to try and find some variable or something we can measure where they connect. And so this is where we're going to be using the fact that volume is 4/3 pi r squared, or not r squared, r cubed, and surface area is just 4 pi r squared. Both of these, so volume and surface area, those are what we're trying to connect, but both of them connect by using the radius. And so that's how we're going to be able to approach going through these, and we are going to solve for the radius in terms of the others. So, for example, if we were to, since we're trying to find the surface area, let's just take the derivative of this first. So we get that ds dt is going to be 8 pi r dr dt. And so dr dt, we are going to solve for using this equation. So from this, we can find that dv dt, by taking the derivative of both sides, is the 4 pi r squared dr dt. Notice that 4 pi r squared is our surface area. So what we really have is dv dt is equal to s dr dt. So dr dt is dv dt divided by s. Now that we have that, we can plug that in to this right here for the dr dt. So we find that ds dt is equal to 8 pi r times dv dt divided by our surface area s, which we could also write as 4 pi r squared, which in this case is probably the way we would want to do it, because then some terms can cancel. This pi will cancel, this 8 and this 4 will cancel, and we're left with a 2 on the top, and then this r and this r squared cancel, and we are left with ds dt is just going to be 2 dv dt divided by r, which is a really concise thing for two things that we didn't see a direct connection between. And so using this, we can then be able to say, if we know the radius, what is the rate that the surface area changes at that specific instant. And so that's how we would be able to approach this problem. Did that answer your question about related rates, or would you like to see some other examples? All right. Any other topics or concepts people would like to go over?
Can we go over implicit differentiation?
Yeah. So implicit differentiation, this is where you can't or don't necessarily want to solve for one variable explicitly. So an example of this might be if we have the relation where we have cosine of x plus y equals y e to the x. This is something that if we had to solve for y would be an absolute nightmare to try and do. Like I personally don't even think it's possible to find an equation where you get y equals some function of x. I don't think there's a nice way of writing that. And so if we're trying to find y prime, we can't just write it as f of x and then take a derivative. That's not something that's going to work out in this case. So instead what we're going to have to do is we are going to just take the derivative of this entire expression with respect to x right at the start. So we are going to just take the derivative of all of this with respect to x, and we are going to treat y as a function of x. And so anytime we take the derivative of y with respect to x, we are going to have a dy dx, or a y prime, pop out. And so if we were to take the derivative of cosine of x plus y, this is going to be a chain rule piece. So the derivative of cosine is negative sine. So we get a negative sine of x plus y. But then we multiply that by the derivative of the inside. So the derivative of the inside is going to be 1, because the derivative of x is 1, plus the derivative of y, so a dy dx. So that's the derivative of one side. On the other side, we are going to have a product rule. So we have the first times the derivative of the second, so y e to the x, plus the derivative of the first, so a dy dx, times the second, e to the x. So that's what just taking the derivative is going to do. Our next goal is to get all of the dy dx's clumped together. So the first thing I would do is I would expand out this side. So I would write this as negative sine of x plus y minus dy dx times sine of x plus y. So that's how I would break that one up, and then the other side would stay the same. And then the next thing that we would want is we want the terms that have a dy dx to both be on the same side. So I'm going to move this to this side by adding it, and then we are going to move this y e to the x to this side by subtracting it. And so once we've done that, we are going to be left with a negative sine of x plus y minus y e to the x is equal to dy dx e to the x plus dy dx times sine of x plus y. And at this point we can factor a dy dx out from everything on this side, and this side becomes a dy dx times e to the x plus sine of x plus y. And this side is staying the same. And so what we can do, so we have the negative sine of x plus y minus y e to the x. We can divide both sides by this e to the x plus sine of y. And so we can just take all of that and drag it under here. And so that's going to be what the derivative is equal to. The dy dx is this. Negative sine of x plus y minus y e to the x all over e to the x plus sine of x plus y. That's going to be how we would take the derivative of this whole thing. This is the same method that we would do to take derivatives of other functions. So for example, if you're ever asked to take the derivative of a logarithm, like for example you say y is equal to the natural log of x, this is one that we've learned by now, but if it wasn't one that we had learned, we can find this by taking implicit differentiation after we've rewritten this a little bit. Because y equals the natural log of x, that's the same thing as saying e to the y is equal to e to the natural log of x, which is equal to x. So we have e to the y equals x, and this is something we can just take the derivative of implicitly. So if we were to do that, we have the derivative with respect to x of e to the y equals x. The derivative of e to something is just e to that thing times the derivative of it. So this goes into an e to the y times dy dx is equal to 1. So dy dx is equal to 1 over e to the y, but e to the y is equal to x, so this is a 1 over x. And so that's how we take the derivative of a logarithm. You take e to the power of both sides, or a base to the power of both sides, and then it turns it into something that we've already learned the rules for how to take the derivative of. And so that's how we can use implicit differentiation in these sort of situations. Did that answer your question with implicit differentiation, or are there other things that you would like to go over?
That's good for implicit differentiation.
Okay. Did you have other topics you wanted to touch on? Okay. So using the mean value theorem? Okay. Are you talking about when you're saying there is one real solution, showing that there exists a solution, or that there is exactly one solution? Because the mean value theorem is only able to be used to show that there's at least one solution. If that's the case, we can definitely go through some of those.
Yes.
Okay. So the mean value theorem, so let's see. So the mean value theorem states okay. Let's see. So the mean value theorem says that if you have a function f of x and it is continuous on some interval and a closed interval from a to b and differentiable on the open interval a to b, then there exists so there's some c where a is less than c is less than b, where the derivative of f at c is equal to f of b minus f of a all over b minus a. Specifically, this is equal to the slope connecting the two endpoints. So here's a, here's b. Our function is doing something like that. The slope of the line is the slope of this purple line right there. And so that's what this is saying. It's saying there's some line connecting the two, and then we can take the derivative of the function at some point somewhere in between, and it's equal to that slope. So, for example, we might be asked to do something along the lines of like show there is at least one place, or let's see. So we might be asked to say, like, show that x, the lines y equals x and y equals e to the x intersect. Oh, actually those don't. The line y equals x plus 5 and no, that's the intermediate value. Okay, line y equals x plus 5 and y equals e to the x have a point C where the tangent to y equals e to the x is parallel to x plus 5. So that is what we would be asked, that's something that we might be asked to do using the mean value theorem. And so what we would need to do is we'd need to find that's a bad question for the mean value theorem. Let's see. Alright, that would be a better one. So a better question would be to ask if we were to ask to show there is a point C where the tangent to y equals 7x squared plus 4 is parallel to y equals 2e to the x. This would be something that the mean value theorem would be able to help us with. So the way that we would approach this is if we were to think of this as graphing it, so we'd have y equals 7x squared plus 4 is something like this, and then 2e to the x would be something like that. So somewhere, probably about here, the tangent lines are going to be the same. And so that's what we are going to be trying to figure out. We're trying to figure out what is the x value where those are the same. Now, two lines are going to be parallel if, when we were subtracting the two functions from each other, the slope was 0. So in other words, we are looking for a point where if we define f of x as 7x to the x squared plus 4 minus 2e to the x, we are looking for a point where f prime of x is equal to 0. Or I guess not x, but c. And so we need to find two endpoints where the slope is going to be connecting the 2 points is 0. So let's see if there's any nice values. I might modify this second function to make some points work out nicely. So for example, at x equals 0, f of 0 is going to just be 4 minus 2, so that's going to be a 2. And let's modify the 2e to the x so that f of 1 is also 0. So f of 1 is equal to 7 plus 4 minus 2e. So that's 11 minus 2e. Let's see, so we want that to be 2. So y is going to be, let's see, so minus 9 minus 2e x. That's how we will modify our function. Okay, because this time if we plug in x equals 0, it's 4 minus 2, so then, let's see, this is now a plus 9 minus 2e x. Oh no, that's very much wrong. Plus, minus. Okay, so there. Now our function is going to actually work. So now if we look at our function at 0 and at 1, we see that f of 0 is going to be 0 plus 4 minus 2 minus 0. So that's equal to 2, and f of 1 is equal to 7 plus 4 minus 2e minus 9 minus 2e times 1, which is 11 minus 2e minus 9 plus 2e, which is equal to 2. So f of 0 and f of 1 both are equal to the same value. And so the mean value theorem, or Rolle's theorem, depending on which one you like more. What am I doing? So both the mean value theorem and Rolle's theorem would apply in this case. And so what we can do is we could say, like, by the mean value theorem, since f of x is continuous on the interval 0 to 1 and differentiable on the open interval 0 to 1, then since f of 0 equals f of 1 equals 2, there is some c with there's some c with 0 less than c less than 1 where f prime of c equals 0, which then tells us that the slope of y equals 7x squared plus 4 at c is the same as the slope of y equals 2e to the x plus 9 minus 2e x. So those are going to both have the same slope at that point c, and we don't necessarily know what it is, nor would we really want to solve for it, but it does exist. Did that answer your question, or would you like to go through something else with this?
Could we do one that asks you to prove that there's one solution? Like the, here, one sec, I'm just looking for it.
Mm-hmm.
Like the one that says, show that the equation has one real solution.
Okay. I think that would be more a problem of like the intermediate value theorem. So that'd be something like you have like y equals x cubed plus 5 and show there's one real solution, or I guess probably f of x. Like f of x is equal to x cubed plus 5, and then show there's one real solution, f of x equals 0, where then you would be able to say like f of negative 2 is negative 3, and f of 1 is 6. So you have at negative 2, it's back, what on earth is going on? So back here at negative 2, it's at negative 3, and at 1, it's at 6. And then since f prime of x is 3x squared, which is strictly greater than or equal to 0, this function is, this tells us that f is always increasing. So that means it can't backtrack. So we'd have some function that would go like this. It could be flat somewhere, but it would never backtrack. And so that would show there's exactly one solution. But the mean value theorem, there is nothing in the mean value theorem that guarantees exactly one solution. So the mean value theorem, all it says that there is some c. The mean value theorem might have more than one value in between that satisfy it. The mean value theorem can only guarantee a single, it can only guarantee that there is at least one. It can never limit the number that there are. That would be something that you would have to use some other theorems in addition to. So something like the intermediate value theorem, or like something's always increasing, those sorts of things. But just the mean value theorem itself does not ever guarantee exactly one solution.
I see what you're saying. In class, we did an example that was like x cubed plus e to the x equals 0, and we used the intermediate value theorem, and then we did a proof by contradiction. Is that what you're talking about, or is that a different thing?
Yeah, that would be this sort of thing as well. So if we had something like f of x is e to the x minus x squared, was that what it was? Or something like that? Let's see, that would be about it.
It was x cubed plus e to the x was the example.
Okay, so if we had something like e to the x plus x cubed, and you're trying to show that there's a point where this is equal to 0, So like showing that there's a point where f of c is equal to 0, something like that?
It just said to show that the equation has one real solution.
Okay. So show one real solution. This is not the mean value theorem. This is the intermediate value theorem. So this is something that we would use the intermediate value theorem on. Which is different from the mean value theorem. So the intermediate value theorem says that if f is continuous on the interval from a to b, then for every like value y in between f of a and f of b, or possibly going the other direction with these inequalities depending on which one is bigger and which one's smaller, there is a c in the open interval, open interval a to b. Is it open? No, this one's closed. Closed interval a to b with f of c equaling that y value. And so this would be the intermediate value theorem application. So for example, we would say that f of, -5, for example, this is 1 over e to the 5th minus 125, which is definitely less than 0. But then if we were to look at something else like f of 0, that would be a 1 plus 0, which is bigger than 0. And so the intermediate value theorem tells us that there is some number between -5 and 0 where f of c is equal to 0. So now we know there's at least one. There might be more. But then to eliminate the possibility of more, we would look at what's the slope of our function f. So we would look at like f prime of x is e to the x plus 3x squared. And so this is something that's always greater than 0. So that means that f is always increasing. Which tells us that there is exactly one solution. So does that make sense how this is using the intermediate value theorem as opposed to the mean value theorem? Yeah, because they are two important theorems, and they both have similar starting conditions, but they do different things. So like the intermediate value theorem does not require us to know it's differentiable. All we know is it has to be continuous. The mean value theorem also requires it to be differentiable. Did that answer your question with this?
Yeah, I think so. I was just a little confused because in class when we did this problem, we proved that there was a solution using the intermediate value theorem, and then we used the mean value theorem to prove that there couldn't be more than one solution.
Would that work? So I am not actually sure how you would approach that using the mean value theorem. The way I would do it would be this sort of method, because the intermediate value theorem is the stuff in red and black, but then this part down here, that is what we needed. We needed to show it was always increasing to know that there was exactly one solution. Oh, that's how you do it. Okay, I see how you're doing it with the mean value theorem then. To do it with the mean value theorem is we would start something by saying something along the lines of assume there were two solutions. Okay, so if there's two solutions, then our graph is going to look something like this, where there's two different places where it intersects. What that then says is between those 2 points, the slope is going to be 0. And so what you would be able to do is then you would be able to say, okay, so assume there's two solutions. Let's call them C and D. So those are our two different solutions. Then we would say, then there is, or let's not call them C and D. Let's call them A and B. So there's two different solutions, A and B. So this point A and this is point B. Then there is some C with A less than C less than B. This is using the mean value theorem, where f prime of C is equal to 0. Because the slope is connecting the two, the slope is 0, so that means there is so somewhere in between there would be a point where the slope of the tangent would also be 0. So this would be using the mean value theorem, or you could use Rolle's theorem. Both of those apply here. But then in our problem, we found that our derivative was equal to 0, or the derivative was e to the x plus 3x squared, which is always bigger than 0. And so this and this give us a contradiction. And this, since this is impossible in our particular problem, that means our assumption that there were two solutions, this was wrong. So we know there's at least one, and then assuming there were two gave us a problem. And so that's how we can show that there's exactly one, and that's how they would have done it using the mean value theorem. Does that make sense? Sorry it took me so long to figure out what you were talking about.
Nope, you're good. Thank you.
All right. Did this make sense, or were there other things that people would like to see involving this? All right. Any other topics people would like to go over or see problems with?
Can we do a curve drawing?
Yeah. All right, so curve drawing, we got this, and let's just toss in a whole bunch of different things. So let's see. So we know that on the interval from 1 to 3, it is concave up. So this means that our second derivative of x is greater than 0. Let's say that from negative infinity to 1, and then from 3 to positive infinity, it is concave down. So concave down, that says that our second derivative of x is negative. We know that on the interval from, let's see, we got negative infinity to negative 1, and then from 5 to infinity, f prime of x is positive, and then that means that from -1 to 5, f prime of x is negative, so it's decreasing, and we know that f of, let's see, f of -2 equals f of 0 equals f of 8 equals 0. So let's figure out how would we graph this. So the first thing I would start is by plotting these points. So f of -2, let's see, let's go back 2. So right there it's equal to 0, at 0 it's equal to 0, and then at 8, 1, 2, 3, 4, 5, 6, 7, 8, it's also equal to 0. So that would be the first thing I would do, and I would make a little check mark on the list to make sure that I know, okay, that's something that I need to keep track of, and I've currently checked off one of my 5 things that I have to do. The next thing I would do is I would gently sketch the slopes, and this is something that I would do lightly with pencil or something beforehand. So let's see. So from -infinity to -1, it is increasing. So -infinity to -1, it is positive. So that's going to be doing something about like that. From -1 to 5, it's decreasing. So going to do something like that. 2, 3, 4, 5. So it decreases to about there. And then from 5 to infinity, it increases again. So that is only taking account those parts. But now we have to figure out the concave up and concave downness. So concave up, remember, is when you are feeling positive, when you're feeling up, you're smiling. So it's making that sort of shape. And then concave down is this sort of shape. And so we are going to have to figure out how can we piece those on to this particular problem. So from 1 to 3, so that is this to this, it is concave up. So if it is a decreasing function and concave up, that means we need to be grabbing stuff that looks like that. So from there to there, it is going to be making that sort of shape. So from here to here, it is going to be doing something generally like that. The next thing is we have from -infinity to 1, it is concave down. And so from -1 to 1, it is concave down and decreasing. So we need it to look like that. So let's get that part in. So that's going to be something, and it has to pass through 0. So let's connect that part. So there's that concave downness. And then it's going to stay concave down but be increasing. So that's going to be something that looks like this. So far we've gotten most of it. We've gotten this part, and then all these things down here. And then the only thing we have left is we still need it to be concave down from 3 to infinity. Let's see, are we able to transition smoothly? From 3 to infinity, it's concave down, so it needs to look like this. But then it needs to start going up. So it's probably going to have to do something like this, where it's going concave down again up until we get to 5. And then it has to switch from being something that looks like this section of the graph to now something that is on this section of the graph. So it's going to then have a very sharp cusp sort of shape and then be going into this sort of concave shape. And once I had all of those pieces, I would then piece all of them together and we would know the graph would look something like we have this, and then it would jump like that. So that would be the general shape of the graph, and anything that looks vaguely like that would get credit for this on the test. So So does that make sense how you're able to kind of piece those different things together to figure out the shape of the graph?
Yeah.
Yeah, like this section here is probably the most complicated, but if you can figure out the different pieces of the different concavenesses, that's the way that I would approach this problem. Yeah, and then the last thing we would probably need to do is to go through and check that we did actually take care of all of them and we didn't miss any. But that would just be a matter of going through each one at a time and making sure that, yes, this is concave up where it's supposed to be, yes, this is concave down where it's supposed to be, and then going through and doing all of those different pieces. And as long as whatever you drew matches all of those pieces, you will get full credit. Because this is not the only graph that looks like that would match. There's a whole bunch of other different graphs that also match it that you would be able to go through and figure out one at a time. Yeah. Any other questions or topics people want to go over?
Can we go over Lhopitals Rule?
Mm-hmm. Yeah, so Lhopitals Rule is something that gets used in one of two cases. So Lhopitals Rule says that if we have a limit as x goes to some value a of f of x over g of x, and if this is basically behaving like infinity over infinity with a plus or minus in front, or a plus or minus 0 over 0, then Lhopitals Rule says that the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of the derivative of f over the derivative of g. So if our limit is in one of these two cases, we can use Lhopitals Rule. So for example, we might have something like, what is the limit as x goes to infinity of, we got x squared over e to the x. So we might be asked, what is this limit? If we just plug in infinity, we are going to get infinity squared over e to the infinity, both of which are infinity. So this is in our infinity over infinity case. So we can use Lhopitals Rule and say this is equal to the limit as x goes to infinity of the derivative over the derivative. So the derivative of x squared, that is a 2x, and then the derivative of e to the x, that is e to the x. And now we can check, is this something that is now something we can evaluate? Well, 2 times infinity, that's infinity, over e to the infinity, that's infinity. So both of these are still infinity over infinity. And so because of that, we can actually use Lhopitals Rule again. There's no limit to how many times we can use Lhopitals Rule. As long as it is one of those two cases, you can continue to use it. So now using Lhopitals Rule, we can take the derivative of the top, which is just 2, and then the derivative of the bottom, that's e to the x. This is now a number over infinity, which goes to 0. And so that's how we can use Lhopitals Rule to evaluate this limit. As long as it's infinity over infinity or 0 over 0, you can use Lhopitals Rule. If it's not one of those two cases, like for example, it's 0 times infinity. So for example, one that is a common one with that is the limit as x goes to 0 of x squared times the natural log of x. This is something that is, or natural log of absolute value of x. This is something that if we were to plug in, this is a 0 times a negative infinity. Well, that is a big problem. 0 times infinity can be literally any number, but we can't use Lhopitals rule on this, because this is not in the form infinity over infinity or 0 over 0. But we can do a clever way of rewriting it, and this is what you will want to do any times you have 0 times infinity. You want to rewrite this so it's either infinity over infinity or 0 over 0. The way I would do this is I would rewrite this as the limit as x goes to 0 of the natural log of absolute value of x over 1 over x squared. Because now this top, this is going to negative infinity, and this bottom is going to positive infinity. And so because of that, we can now use Lhopitals rule. This is now infinity over infinity. So, using Lhopitals rule, this is going to be the limit as x goes to 0 of the derivative of the top, so the derivative of the natural log of x, that is a 1 over x, and then the derivative of 1 over x squared, that is a negative 2 over x cubed. So this is equal to, we have the limit as x goes to 0 of 1 over x divided by negative 2 over x cubed, so that's times x cubed over negative 2. So this is equal to the limit as x goes to 0 of negative 1/2 times x squared, which goes to 0. And so that's how we would be able to use Lhopitals rule in this situation to be able to evaluate this limit. Any other questions with Lhopitals rule or things that you would like to see with it?
Can we do some trig?
Yeah, we can do this with trig as well. So, for example, a common trig limit that we see, so which you can actually do without Lhopitals rule, but it's the easier way to figure it out. So for example, the limit as x goes to 0 of cosine of x minus 1 all over x. If we evaluate this at 0, we get 0 over 0, but we can use Lhopitals rule and show that this is going to be the limit as x goes to 0. The derivative of cosine, that's negative sine, so we have a negative sine x over the derivative of x, which is 1. Plug in x equals 0, this gives us 0. So that's one way we can do that one. We could also do the same thing with sine x over x, and you would be able to use Lhopitals rule there. Yeah, you're able to use Lhopitals rule anytime you have a situation where you have 0 over 0 or infinity over infinity. Any of those sorts of limits you can do using Lhopitals rule. And so that's how you would be able to approach them. Would you like to see some others, or are there specific limits you want to try, or is that good enough for now? Okay, any other topics anyone wants to go over? Yeah.
I was just wondering if we could do the limit as x approaches 0 from the right of arctangent of 3x over the natural log of x.
Let's see, arctangent of 3x?
Yep, over the natural log of x.
Yeah, we can do that. So arctangent of 3x, that is, let's see, arctangent of 0. So let's see, so arctangent of 0, that is inverse tangent of 0. Let's see, so that gives us some value theta where 0 is equal to tangent of theta. And so that is going to happen along this line here. So when theta is equal to let's see, and then arctangent is only on this side, so theta is equal to 0. So this is going to be something that's 0 over, let's see, natural log of 0, that's going towards the negative infinity. And so this one's just going to be 0. Because 0 over infinity is going to 0. So this would not be one that we would be able to use Lhopitals rule on, because it is not 0 over 0 or infinity over infinity. But that's how I would approach this problem. I would figure out what's the top do, what's the bottom do, and then if there's some situation that comes up that's hard to deal with, then I would go a little bit deeper into this. But because this one is 0 over an infinity, that's just going to go to 0. Does that make sense?
Yes.
Okay. Any other topics anyone would like to go over?
Can we go over derivatives of log functions?
Yeah. So let's say that we have y is equal to log base b of x. And we're trying to figure out what is y prime. So what's the derivative of y with respect to x? If we have a log function and you don't remember the rule, the way we can do this is we can rewrite this as an exponential and then use implicit differentiation. So this is the same thing as saying b to the y is equal to x. So just take the derivative of both sides, or we just raise both sides to the power of b. Wait, no. We do b to the power of both sides, and we are able to get it as b to the y equals x. And then we can take the derivative of this. So if you remember the derivative of b to the y, that's great, we can do that. If you're like me and never remember that one, what we would have to do is we would have to rewrite that in terms of e to something. So a useful thing to remember is that b to the y is equal to e to the natural log of b to the y. So that's just something that you can always hopefully remember, that like x is equal to e to the natural log of x. So b to the y is e to the natural log of b to the y. And so once we have that, we can then use some exponent rules in the b to the y part to be able to then say that means that b to the y is equal, because we can bring this the exponent out of the natural log, so that's e to the y times the natural log of b. And so this gives us a form that we can be able to take the derivative of using the chain rule and stuff. So then we are able to say that means that x is equal to e to the y times the natural log of b. And now when we take the derivative of everything with respect to x, now it's just a matter of remembering the chain rule to figure out what that's going to be. So the derivative of x with respect to x is 1, and then the derivative of e to the y times the natural log of b, well, e to something is e to that same thing times the derivative of the inside, which is going to be the natural log of b times dy dx. And so what we can then do is we can now work backwards and try and solve for dy dx. So e to the y times the natural log of b, that's the same thing as b to the y. So we get 1 equals b to the y times the natural log of b times dy dx. But b to the y is the same thing as x. So this is equal to x times the natural log of b times dy dx. So solving for dy dx, that then tells us that dy dx is equal to 1 over x times the natural log of b. And that is how you are able to take the derivative of a logarithm. You rewrite it in terms of an exponential and then use implicit differentiation to take the derivative of both sides. Does that make sense?
Yeah.
Okay. Any other questions that anyone has?
Can we go over rate of change in the sciences?
Yeah. So, in different subjects, there's a whole bunch of different things that are all different rates of change. So, for example, in physics, this is where the most direct connection that most people can see comes from. So if we have like s of t is our position, then there's a whole bunch of different derivatives that all have a very like specific meaning in physics. And so like the derivative of position is going to be, so like s prime, this is velocity. S double prime, that's acceleration. We can take the third derivative. Just a side note, if you ever see an exponent where the number is in parentheses, like this, it's like this, that is saying the third derivative, which is not the same as saying s to the 3 without the parenthesis. So the parentheses say this is like some number derivative. So the derivative of acceleration, this is jerk. And it actually keeps going, so like s, the fourth derivative, this is snap. The fifth derivative, this is crackle. And then the sixth derivative, as you might have guessed, this is pop. So physicists do actually have a sense of humor, which is nice to hear. So like those are some of the derivatives of physics. So if you're ever asked to find one of those things, usually dealing with some of the things up here in the earlier, more well-known names, you would just have a couple derivatives you might have to take of your position function to figure it out. Other things that they come up with that show up is, for example, in biology, you might have something that represents population growth. So this is just the derivative of population with respect to time. So that's something that we care about. If a population is growing too fast, that might cause problems. If a population isn't growing fast enough, then that means that we might overfish the population and drive it to extinction. Those are things that we care about. We need to know what's happening with those sorts of things, and so those are things that show up. Other ones that are on the top of my head are like in economics. There's what's called marginal cost, which is in economics like the cost to produce one more thing. This is equal to the derivative of your cost function with respect to not time, but with respect to like x, where x is the number of items made. So like those are things that show up in economics. Like there's the like rate of reaction in chemistry, so that's the derivative of the reaction as the reaction speed as a function of time. So those are different things that show up, but most of them are just figuring out what's the function and what's the derivative mean, and those are the sorts of things. So a lot of this is just interpretation of derivatives and how you're able to do things with that. Did that answer your question with like rates of change?
Yes, that does answer our question. Thank you.
Okay. And I saw someone asking to find inflection points. So inflection points these are places where the second derivative of a function is equal to 0. So these are points where it's possible for it to be transitioning from concave up to concave down. So if we were given a function like f of x equals 3x cubed minus sine of x, we would need to take two derivatives. So our first derivative would be 9x squared minus cosine x, and then our second derivative of x would be 18x plus sine x. And we need to solve where is this equal to 0. Let's see, one place where this is 0 is x equals 0. That would be one point of inflection. I picked a bad function because it's hard to solve for other ones. But this is one place where the second derivative is 0, and so that's one of the inflection points. It's not always going to be a point where it does transition from concave up to concave down. Like you might have something where it goes like this, and then, let's see, what would it transition to there? But yeah, so like these points where the second derivative is 0, those would be inflection points. And so that's how you would find them without graphing. You just calculate what's the second derivative and see where is it equal to 0 or where does it not exist. Did that answer your question about how to find inflection points? All right. Does anyone else have any other topics or questions they want to see? I know some of your sections are going over Newton's method right now and last week. Is that something that you would like to go over, or is that something that is specifically waiting until next test?
That's going to be on the next test.
Okay. Yeah, that one is always a confusing one to understand, so I just wanted to make sure that we touched on that if it was going to show up on your test. But yeah, any other topics that people want to go over? Yeah, we can go over finding local mins and maxes. So there are a couple ways that we can find mins and maxes. So the first thing that we would need to do in any situation is we need to find our critical points. Once we have our critical points, so these are where either our derivative of x is equal to 0 or the derivative of x does not exist. Those are going to be our two ways that we can get critical points. We can then either go to what's referred to as the first derivative test, or we could go to the second derivative test. So both of them have pros and both of them have cons. So depending on the situation, one might be easier to do than the other. So the first derivative test says that once you have all of your critical points, the way I would do it is I would then basically like plot a number line, and then 3, you test points between each set of critical points. to determine if your derivative of x is greater than 0 or less than 0. So basically you're figuring out, is it increasing before and then increasing before and decreasing after? That's what the first derivative test would be doing. So like for example on a number line you might have like these critical points. So we have like a critical point here, we have a critical point here, and we have a critical point here. And then if we were to figure out what is the first derivative of x, and we test different numbers on either side, so not testing the critical points themselves because those are all 0 or don't exist, but then we test, oh, it's positive here, then negative here, then positive here. What we can do is we can say, well, right here, this is neither. This is not a maximum nor a minimum. However, this one right here, this increases and then decreases. So this one's going to be a maximum. And then this one here, this decreases and then increases. So this is going to be a minimum. And so that's how we would use the first derivative test to figure out local mins and maxes of the function. The second derivative test, once we have our critical points, the next thing we would need to do is we need to calculate f double prime of x. We need to find the second derivative. Then after that, we would evaluate our second derivative of x at the critical points. And then at this point, what we would be able to say is if f double prime of our point C is greater than 0, this is positive, this is going to be concave up. So this is going to be a minimum. And then if f double prime at our critical point is less than 0, this is concave down, which is a maximum. If it's equal to 0, then we're just like, I don't know what that is, because the second derivative test didn't tell us anything. And so then we might need to go back and actually do the first derivative test if you would prefer, to be able to figure out, is it a maximum or a minimum? Something that confuses people fairly often about the second derivative test is why when the second derivative is positive, is it a minimum, and why is it when it's negative, it's a maximum? If it's positive, the way I remember it is if you're feeling positive, you're probably going to smile. So it's going to be something like that, and so that tells us it's a minimum. Whereas if you're feeling negative, you're probably going to frown, so it's going to be something like that, and so it's a maximum. And so that's a little mnemonic that I use to remember them, but that's what you would do to find the minimums and maximums of a function. You first have to find the critical points, so you always take the derivative and set it equal to 0, and solve for any x values where that's the case, or where the derivative does not exist. And then you can either do the first derivative test or the second derivative test from there. Did that answer your question? All right. Any other questions that anyone has? I guess one more thing going along with finding the minimums and maximums is both tests work most of the time. There's only a couple situations where one test will work and the other test won't, but most of the time they both work at the same situations. So if there's one test that makes the most sense to you, use that one most of the time. However, the one that makes the most sense to people most is usually the first derivative test. But imagine what would happen if your critical points were at 0, 1/64th, and then maybe at 1. To figure out if 0 and 1/64th are maximums and minimums, you have to test a number in between 0 and 1/64. And so those sorts of numbers might be hard to evaluate and figure out, is this positive or is this negative, especially if you're having to do it without a calculator. In these situations where they're close together and it's hard to calculate is it positive or negative, those situations are ones where the second derivative test might be a lot easier to do. And so keep in mind that just because you usually do it with one of the tests, the other test might make your work easier to do, or something that is more straightforward to be able to accomplish. So that's just something to keep in mind when you're trying to find maximums and minimums. Yeah. Any other questions anyone has? What do you mean by like LP rule questions? Is that like Lhopitals Rule? Okay. So yeah, so with Lhopitals Rule, let's see, where was that when we were doing that earlier? So yeah, so with Lhopitals Rule, the main thing is that in order to use Lhopitals Rule, it has to be infinity over infinity or 0 over 0. If it's not one of those two forms, you usually have to figure out how can I rewrite this into that form. So like we went over some situations where you have something like if it's 0 times infinity, rewrite it so it's infinity over infinity. So for example, x squared times the natural log of x, that's a 0 times infinity. So rewrite it as natural log of x over 1 over x squared. Then it's infinity over infinity, and we can use Lhopitals Rule. The other situations that you might run into, which are usually the more complicated ones, would be if you are in the form of like a 0 to the 0, 1 to the infinity, or like infinity to the 0. One of those situations. These are ones that are also hard to do. So let's say, for example, we have the limit as x. What? Where did everything go? Okay. So let's say that we were dealing with something like the limit of e to the x no, that's not one though. Yeah. Let's see. These ones are the hardest ones to come up with examples for because they're the nastiest ones to try and deal with. Let's see. So we have 1 plus 1 over x raised to the x as x goes to infinity. This is of the form 1 to the infinity, because as x is at infinity, the 1 over x goes to 0, and then the x goes to infinity. So this is one we're like, well, it's 1 to the infinity. This isn't a L'Hopital rule problem, because it's not infinity over infinity, but it turns out that we can manipulate this to turn it into a L'Hopital rule problem. So assuming that this converges, we are going to say that this is equal to L. So it's equal to some limit. We don't know what it is, but we're going to try and solve for L. The next thing we're going to do is we are going to take the natural log of this entire thing. So this turns into the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x is equal to the natural log of L. At this point, we're going to do some natural log manipulations of 1 plus 1 over x to the x. Because we have this exponent, we can bring it out front. So this is now the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. And this is now something that we might try. Okay, what happens if I plug in x equals infinity now? Now this is in the form infinity times 0. Great, still indeterminate form. So this is something that we now need to figure out. Can we manipulate this to turn it into a Lhopitals Rule problem? Well, we need it to be infinity over infinity or 0 over 0. Well, moving this to the bottom feels like a mess. So we don't probably want to try the infinity over infinity, but we can try and turn it into a 0 over 0. So we can show that this is equal to the limit as x goes to infinity of, so we don't want to move natural log of 1 plus, what on earth is going on today? Okay. So we don't want to move the natural log of 1 plus 1 over x to the bottom, because that would be a nightmare to try and do. So to move this equal to something, if we have an x on the top, that's the same as putting a 1 over x on the bottom. And now when we check, this is in the form 0 over 0. And so now this is in the form where we can do Lhopitals Rule. So this is equal to, using Lhopitals Rule, the limit as x goes to infinity of the derivative of the top. So that's going to be a 1 over the bottom, 1 plus 1 over x, multiplied by the derivative of the inside. So the derivative of 1 plus 1 over x, that is a negative 1 over x squared. So that's the derivative of the top. And then the derivative of the bottom, 1 over x, that goes to a negative 1 over x squared. Oh, lucky us, we have stuff that cancels. So this negative 1 over x squared will cancel with this negative 1 over x squared there. So we're left with just the limit as x goes to infinity of 1 over 1 plus 1 over x, which is 1 over 1 plus 0. So this is equal to 1. Yay! We found that the limit was 1. However, that was this limit. So that tells us that 1 is equal to the natural log of L, which tells us that L is equal to E. So that is probably the most complicated type of a Lhopitals Rule problem that you might come across. So if it's in these indeterminate forms where you have exponents of numbers like 0 to the infinity, 1 to the infinity, or 0 to the 0, 1 to the infinity, or infinity to the 0, take the natural log of everything. It'll then turn it into the product, one of the product indeterminate forms, so 0 times infinity. And then you try and manipulate that to turn that into a Lhopitals Rule problem. And so that's how you would be able to figure out these sorts of things. Does that make sense? Okay. Any other questions that anyone has? Yeah, we already covered the mean value theorem, but we can go over it if you want. Alright, so the mean value theorem says, let's see, we got it up here. Alright, so the mean value theorem is this. It says that if our function f is continuous on the closed interval a to b, and it's differentiable on the open interval a to b, then there is some point in between a and b where the derivative of the function at that point c is the same as the slope that connects the two endpoints. So what that means is if you know two endpoints, then you're able to find the slope and you're able to go through and do stuff with that. So for example, some things that you might be asked to do is to, for example, show that in your interval -1 to 6, there is a point C where the derivative of, let's see, the tangent to f of x equals x squared plus 2x plus 1 with a tangent line to that function has slope of, let's see, 36, 48, 49, has slope of 7. I am impressed with myself for picking one that had nice numbers come out. Okay, so the mean value theorem says, first we need to check, is f continuous on the interval -1 to 6? Well, turns out the answer is yes. Perfect. That means the first condition of the mean value theorem is working. The second one is f differentiable on the open interval -1 to 6? This one is also a yes, because it's a polynomial, f prime of x, that is just 2x plus 2. Perfect. Like, we're able to take the derivative, it applies. So that means the mean value theorem says, let's try and keep that on screen. Yeah, let's go this way. So that says that the mean value theorem says that thus there is some c with -1 less than c less than 6 where f prime at c is equal to f of 6 minus f of -1 all over 6 minus -1. Now, we're going to hope that this is equal to 7, otherwise the mean value theorem doesn't help us with this problem. But if we evaluate that, see f of 6, that is 36 plus 12 plus 1, minus f of -1, that's 0 all over 7. 36 plus 12 is 48, plus 1 is 49, so this is 49 over 7, which is equal to 7. Perfect. The mean value theorem tells us that there is a point in there where the slope is equal to 7. The mean value theorem doesn't tell us where it is. The mean value theorem doesn't tell us if there's more than one, but the mean value theorem tells us that there's at least one, which is all that we really needed for this problem. You can also use the mean value theorem on problems like, so the problem we were doing earlier was an example where we were trying to show that there is exactly one solution to a function. So we were trying to show that there is exactly one solution to where f of x is equal to e to the x plus x cubed. We were trying to show that there is exactly one real solution to this. So first we had to start by using the intermediate value theorem to be able to show that there's at least one solution. So the intermediate value theorem, that's this right here, says that if f is continuous on a to b, which is less specific than the mean value theorem, because the mean value theorem also requires differentiable, the intermediate value theorem just requires continuous. So if f is continuous on the interval, then for every output in between, there is an input that gives us that output. So in a diagram, the intermediate value theorem says that if that is one endpoint and this is another endpoint, if I pick some point in between, so calling this some value, no matter what my continuous function is, it has to pass through that line at least once. It's not possible to go from one endpoint to the other without crossing the line. Now, that's really intuitive. It's basically the theorem that says if you draw a line, you have to cross something. But it's a pretty powerful result. So in this problem, if we were trying to show that there's exactly one solution, first we have to show there's at least one solution. So the way we would do that is we just need to find something that is below 0. So in our case, we said x equals -5, and then something above 0, which is x equals, I believe we used 1. No, we used 0. So x equals 0 is positive. So this is a positive number, this is a negative number. Somewhere in between there was a number where it was 0. And so that's all the intermediate value theorem was able to tell us. It tells us that there is at least one solution. We can then use the mean value theorem to show that there's exactly one solution by starting by assuming there were two solutions. So if there were two solutions, so A and B, so two places where it was equal to 0, that means we have something kind of like this diagram, where at A and at B, both of those, there is some, both of those intersect the x-axis. So that means that both of them, y is equal to 0. And so then, since our function is continuous and differentiable, we were able to then say, if we had two solutions, then the mean value theorem tells us there is a point where the derivative is equal to 0. Because if the slope connecting the two solutions, that slope is 0, there is somewhere in between where the slope is also going to be 0, or the tangent line is 0. However, when we calculated the derivative, it was e to the x plus 3x squared, which is something that is always bigger than 0. And so because of that, that tells us that we were able to guarantee that there was exactly one solution, because assuming there were two solutions caused a huge problem. And so that's how we're able to do some different problems with the mean value theorem. Did that make sense to you, or would you like to go through some other problems and stuff with this?
So just a quick question.
Yeah.
So the reason that it's always increasing is because it's 3 to the x squared and e to the x. Mm-hmm. Is that why?
Yeah, because e to the x is something that's always positive, and then 3x squared is never negative. Like 3x squared can be 0, but 0 plus a positive is still positive. So that's why it's never equal to 0.
Mm-hmm. Okay, and so this is basically, because I'm guessing this is going to be one of the written portion questions.
Quite likely.
Yeah. And so basically, if I have just kind of what you have written down here, as long as I write all of that out, applicable to the question, that should get me full points, right?
Yes, probably like more detailed words than I did, but yes. Like that, the basic gist of these sorts of problems is you first have to show that there are solutions, and so that is going to be doing the intermediate value theorem. Show that there is at least one solution. The next thing is to use the mean value theorem. So first, use intermediate value theorem. Second, ignoring this wrong thing right here. Second, you're going to assume there are two solutions. So intermediate value theorem guaranteed there's at least one. So the next thing we do is we say, okay, I'm going to assume there are two solutions. If there are two solutions, then I can use the mean value theorem. And then the mean value theorem is going to conclude that there is a point where the slope is equal to 0. Next, I'm going to actually compute what is the slope, and I'm going to show it can't be 0. And that's going to give me a contradiction, which told me that my assumption was incorrect. And so if my assumption that there were two solutions was wrong, if I have at least one solution and there can't be two or more solutions, that means there has to be exactly one solution.
Okay.
So those 6 main things are going to be the bulk of this problem. You're asked to show there's exactly one solution. Use the intermediate value theorem, show there's at least one. Next, assume there's two. Use the mean value theorem to show that there's a point where the slope is 0. Show that the slope can never be 0. Therefore, there has to be exactly one solution.
Ooh. Okay. That makes actually a lot of sense.
Awesome. Do you have any other questions?
Honestly, not really. I feel like I just want to practice more than anything. So I'm going to go do that.
Okay. Good luck on your
All right.
test.
Thanks. Have a good night.
You too.
Bye.
I hope you enjoyed this video and that it was helpful for you. Please check out some of my other videos, and please like and subscribe if you have not already so I can continue to make these sorts of videos. Have a great day and good luck with the rest of your math.